Hello students, so let us continue our sessions on this tutorial problems for the fourth unit. So if you remember previously, we solved a similar kind of problem where we had a series resistor between the transmission lines. Right now what we have is a shunt resistor or some kind of circuitry between two transmission lines. So whenever you have such kind of circuits, all you have to do is to find the voltages and the currents that are entering or leaving into the circuit, and you can apply your normal circuit theory to find the unknowns. So that is a procedure in most of the cases. And you can see here, you're imagining that in this region there is no transit time effect and you can apply the network theory, but outside this region there are transmission lines, and here in fact you can see that the voltage and current equations on these two lines are given. So this is the voltage equation on the first line, and this is the voltage equation, total voltage equation on the second line. And because the voltage at any point on the line is given, and in fact these equations are defined with respect to two axes, Z1 and Z2. So the first line, for the first line the voltages are defined with respect to Z1 axis, and for the second line the voltages are represented with respect to Z2 axis. So according to the Z1 axis, so if this is your forward wave, then this will be your backward wave, and according to the Z2 axis, so because usually take a wave in the direction of Z2, so that's a forward wave, and this will become your backward wave in Z2, right? So if that is the case, let us with those things, what are given here is the voltages are given. So they're asking you to find what is the value of this constant A along with what is the value of the characteristic impedance Z0. So let us try to solve it. So first let me write the expressions for the voltages that are given. So V1 of Z1 is given as 3 into e power minus j beta Z1 minus of 1 is 1 times of e power plus j beta Z1. So if this is the voltage on the line, I can write the current as, for the forward wave it is divided by Z0, so it becomes 3 e power minus j beta Z1 by Z0. Okay, so that is Z0 1. And for the backward wave, so here you can see that this is, I can write the same thing as plus of minus times of this thing. So this whole term is your backward wave. So this is your backward wave VB minus of Z1, and I can say this is V forward wave, right, or V plus of Z1. So it is nothing but the summation of forward plus a backward wave. So that is your whole backward wave. What you have to do for the whole backward wave, you have to divide it by, you divide a backward wave by minus Z01. Okay, so if you do that, you can see that this minus and minus gets cancels out, and you've left with plus Z1. And what is Z01? Z01 is given as 40. So I can put a 40 here. So this is the current expression which I have as a function of Z1. So let me write the expressions for V2 of Z2. So why this is a forward wave? Because you have e power minus j beta z factor that indicates the phase is shifting towards the right. So that gives you a wave that is traveling forward. So that makes a wave. In the same way as you're increasing the z, okay, this shift makes you to go back. So this becomes your backward wave. So in the same way, for the second wave also, if you take a e power plus j beta z2, so as you increase z2, means if you're moving in the z2 direction, I can see that the wave becomes a backward wave. So because the shift will be in the right direction, okay, so that makes you a backward wave with respect to the z2 axis. So this becomes a backward wave. So if it is a backward wave, then the current is simply a times of e power plus j beta z2 times z02 minus z02. So you get a minus because it's a backward wave. So this is your expression for voltages. So let me write what is the value of voltage and current at the boundary condition. So here there are two boundaries. So let me put those boundary conditions. So what is V1 voltage at Z1 equal to 0? So that value is nothing but you have to put z1 equal to 0 in this case. So e power 0 is 1. So you get 3 minus 1, that is 2. In the same way, if I want the current at z1 equal to 0, I can see that the answer is 3 by 40 plus 1 by 40. Okay, so the answer is 1 by 10 amperes. So that is the current. And what about the voltage at z2 equal to 0? So that is this other boundary condition. Excuse me. So this is my other boundary condition. So if I put z2 equal to 0, for z2 equal to 0, you can see that from the first equation it is equal to a, and whereas from the second equation I2 at z2 equal to 0 is nothing but minus a by z02. So these are the values I get. So unknowns are a and z02. So if I get the values and the boundaries, at the boundaries if I know the values of voltage and currents, so let me draw the equivalent circuit now I have. Okay, so I'm erasing the equations, voltage equations I have. So what is the equivalent circuit I have now? So the equivalent circuit I have is like this. So I have a resistor which is in shunt, which is of 100 ohms, and here the voltage is, because it is z1 equal to 0 location, so this is z1 equal to 0 location. For z1 is equal to 0, I have 2 volts, and I have a current that is entering in like this, which is 1 by 10 amperes. And because here the current is coming inward like this, okay, so let me, okay, let us put the terminal so that we don't get. So this terminal is z1 equal to 0 and this terminal is z2 equal to 0 terminal. So at this terminal I have the voltage as A, and of course the current that is coming in is given as minus A by z02. So I have to follow the convention which is given here. So as I can see, because it's a shunt element, this gives me an answer, because whatever voltage I have, the same voltage will be here because there is no series element here. So I can say A is equal to 2 from the circuit, and if I take the current at this node, what is the current that is going into this node? Because the voltage here is 2 volts, the current that is going into that branch will be 2 by 100, right? So it's V by R, and in this direction a current is coming of 1 by 10, and I can say in this direction a current of minus A by Z02 is coming. So from the nodal analysis I can say 2 by 100 should be is equal to 1 by 10 minus A by Z02. Of course it's plus of minus A by Z02. So you get plus of minus, you get a minus sign here. So you get 1 by 10 minus Z02. Okay, so from here if I have to find the value of A, first of all the value of A is given as 2. Okay, so let's try to find it out. So what we'll get, so we get from here, so what is the value of Z02 we need to know. So this is okay, so it is 2 divided by, so you need to get, if you solve this equation you need to get an answer of Z02 is equal to 25 ohms. Okay, so of course the answer is not the final one, that is important. The procedure that you have followed is important one to understand here. So this is how you solve the problem. We have the value of A as well as the value of Z02 also. So let's move on to the next question. So here in this question, the question asks for what is the maximum power that is delivered to the load ZL. and what should be the value of ZL in order for a maximum power to be delivered. So the length of the line is lambda by 8. Okay, so as I have mentioned many times in the course, okay, in order to have maximum power transfer, it doesn't mean that you need to minimize the reflection. So some power is incident like this, and if you can remove the reflected power, that doesn't in general give you a case where a maximum power is transferred. It is not about uh, minimizing the reflection. It is all about making this input impedance Zn is equal to Zg conjugate. Okay, if you can make that, then maximum power is transferred from the load, or sorry, maximum power is delivered by the source. Means the source will deliver the maximum power or its available power, as I said previously. When this conjugate happens, the total available power from the source is delivered, right? So because if you have a circuit like this, Vg, and there is Zg, and here you have something which is Zg conjugate, and if you ask me what is the power delivered to this impedance, it is simply half times of the real part of, means the time average power. The real power is half times of or second bring half out, means if it is if I'm doing it in sinusoidal excitations, of course everything here is a sinusoidal excitation, so you get a half and V into I conjugate. So what is the voltage there? The voltage there is Zg conjugate times Vg by, right, by Zg plus Zg conjugate times okay, so this is the voltage, and what is the current? Current is nothing but current conjugate you need to take. So the current is Vg divided by Zg plus Zg conjugate, because you need to take the conjugate of this. So this is the power that is delivered to this Zg load. Okay, so how much is this? So this value, you can see it is real part of Vg into Vg conjugate is nothing but modulus of Vg square divided by Zg plus Zg conjugate, and you have another whole conjugate here, so that gives you the magnitude square. Okay, so you have some complex number, or I don't know whether it's a complex number, so it's a, so because you take it will be a real number anyways, because Zg if I take as Rg plus Jxg, and Zg conjugate simply becomes Rg minus Jxg. So let us put those values here, but before putting it, so you have here Zg conjugate, so this is your, so half times of real part of modulus of Vg square. You can see if I add these two, I get 2 Rg, so I get 4 times of Rg, and Zg conjugate is nothing but Rg minus Jxg. But you can see I only want the real part of it. So of course this is whole square, so you get Rg square in the denominator. So if I want the real part of it, so this simply becomes Vg square by 8Rg. So this is the available power, or this is the maximum power that you can get when you do this condition. So if you deliver, means if you can match this condition, that whole power, that is the maximum available power from the source, is Vg square by 8Rg. On an average, this much amount of power will be entering into this circuit, and ఈ port నుంచి from this port on an average this much amount of power is entering. It doesn't mean that this is the power that is entering. Okay, it means there is, what I'm trying to say here is, there is some power that is entering forward, an average power that is entering forward, and there can be some power that is reflecting back. So if you subtract this to P plus plus P minus, that will be equal to P available power in this scenario. That is what I'm saying. So I'm not saying the power that is carried by the forward wave itself is this available power when Zg is equal to Zg conjugate. What I'm trying to say here is that on an average this much amount of power is entering, because this line is lossless. No power will be delivered, means it will not eat any power. So overall the load will get a power of modulus of Vg square by 8Rg. right? So with that, let us try to find first, to calculate the power. First of all, we need to calculate the value of ZL, because I know what is the maximum power that is going to be delivered, because the value of RJ is given and the value of VJ is also given. So it is, if I can do this, if I can achieve Zn is equal to Zg, if I choose a ZL such that Zn is equal to Zg, then the power that is delivered is nothing but modulus of Vj square, that is 1 square divided by 8 times of the real part is 100. Okay, so it is 1 divided by 800. Okay, so I can say it is around 1.25 milliwatt. Okay, so that is the power that will be delivered, maximum power, but for what value of load ZL? So that is another question which we need to find. So what is the input impedance formula? So the input impedance formula is Z0 times of ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Okay, so here, because the length of the line is given as lambda by 8, so let us write what is beta L. Beta is 2 pi by lambda times the length of the line is lambda by 8, so you get a pi by 4. Okay, so you get a pi by 4. So if beta L is pi by 4, so here in this place I can put a pi by 4 and a pi by 4. I can see that that simply ends up, because tan pi by 4 is 1, so you get ZL plus JZ0 divided by Z0 plus JZL. Okay, so I can so what I want to find is, I have to find uh, this value here ZL, because ZL can be a complex number. So let me write ZL as some RL plus JXL, and let us substitute the values. So Zn should be equal to Zg conjugate. So that is when I can, for that value of ZL is what I'm looking for maximum power transfer. So Zg conjugate is like this, 100 minus J50. So that should be equal to Z0 is 50. 50 times of I can say it is ZL I have written as RL plus JXL plus J times of 50 divided by 50 plus J times of RL plus JXL. So I can see that from here I have to solve these unknowns by equating the real and imaginary parts. So if I can write this, if I cancel out the 50, so this simply becomes 2 minus J is equal to RL plus J times of XL plus 50 divided by 50 minus XL plus J times of RL, right? So let me multiply these two factors, so then I get 100 minus 2XL plus J2RL minus 50J plus JXL. Okay, then you have a J into J minus 1 and you get a plus. So plus RL. This whole thing should be equal to RL plus J times of XL plus 50. Okay, so I have a big equation. So let me equate the real and imaginary parts there. So the real part equation is like this. So I can see one side there is RL. So this is real part. Okay, so let me equate the real parts. So I can see that 100 minus 2XL plus RL should be equal to RL. Okay, so that is one equation. Then the other equation is this imaginary parts. So I can see that 2RL minus 50 plus XL should be equal to XL plus 50. So that is another equation. So I think from this equation RL gets cancels out. So it gives me that XL should be equal to 50. And if I cancel out these things, so here I can see that XL cancels out. So again I get RL also is equal to 50. Okay, so you can see that when the both are 50, then you'll get an answer. Okay, in fact you can check it also, it works out. So I got an answer for excellent. So if this impedance ZL is taken as exactly equal to 50 plus J50, okay, then at the input I will have an impedance of 100. The impedance will be exactly 100 minus J50. If now this is the case, this is the power that is going to enter on an average, and that power is going to be delivered, and so the power that is delivered is 1.25 milliwatts. So those are the answers we have. So let's move on to the next question. So in this question, of course it is the same kind of question with some impedance given and some line ZL with with some Z0 line, which is a lambda by 4 line. So let's see the first question. If ZL is 49, so if ZL is taken as 49, determine the value of characteristic impedance Z0 that will maximizes the power absorbed by the load. Okay, so what I want is, so if I take ZL equal to 49 ohms, okay, so what should be the value of Z0 so that, okay, so that this Zn, in order to have maximum power, that should be equal to Zg conjugate. But what is Zg? It's a real number, so I need a value of Zn is equal to 25 ohms. Okay, because it's a lambda by 4 line, if you remember, or you can also derive that it is Z0 times of ZL plus JZ0 tan beta L, and divided by Z0 plus JZL tan beta L. And because the length of the line is lambda by 4, so beta into L is 2 pi by lambda into lambda by 4, you can say it is pi by 2, and tan pi by 2 goes to infinity. So if you take the limit goes to infinity, you will end up with an answer of Z0 square divided by ZL. Right, so I think that's what we have done previously. So that is a Zn value. So what I want is the Zn should be equal to 25 ohms. Okay, and the Z0 square is given as, is what is the unknown which I have to find. So this is 25, and ZL is taken as 49. Okay, so that gives me Z0 as square root of this, which is 5 into 7, that is 35 ohms. So that is our first case. So in this scenario, what happens, you will have maximum power that is transferred to the loads. And what is the maximum power is nothing but the available power from the source. So that is modulus of Vg square divided by 8 times of Rg. Okay, so the power that is delivered is given by uh, so this is the maximum power, okay, which I am doing here. If you have to calculate the actual power, then you have to go with the power expressions. That is one way of doing it also. You can derive it from the power expressions which I have given you. So the power that will be delivered is this thing. So here Vj is given, so it is modulus of 10 square divided by 8 times of the Rj is 25. Okay, so it is 100 by 8 into 25. Okay, so it is 0.5 watts. So this is the maximum power that is delivered. So the next question is, if I take Z0 as 50 ohm, so if I'm fixing the value of Z0 now. So the next scenario is I'm fixing Z0 equal to 50, and then I'm asking you for what value of ZL I can have maximum power transferred. Okay, so of course, because it's the still same lambda by 4 line, okay, it is still the same lambda by 4 line, the Zn should again be equal to 25. Okay, and but the Z0 is given here, so now the Z0 is 50 square, and you need to find what is the ZL value, right? So this is your input impedance. So input impedance Zn is equal to, you have Z0 square by ZL. So now Z0 is given, and Zn is a Zg conjugate, which is 25. So from here I can see ZL is nothing but 50 into 50 divided by 25, which is nothing but 100 ohms. So I can see that this ZL will be 100 ohms. Now you might ask me, before the scenarios were different. Before, if you remember, this was 49 and this was 35. In that case, the power delivered was zero point 0.5 watts. If you ask me what is the power delivered in this case also, I will tell you that the answer will be same again. Okay, but this is not the question asked for. Of course, the power is not going to, what is the power that is delivered to this or absorbed by this load is again 0.5 watt only. You might say, sir, the load has changed. Not only load, the characteristic impedance also has changed in order to maintain the same input impedance. So the same power will be delivered to the load. But the question asks for not the power delivered to the absorbed by the power or the absorbed power of the load. The question asks for what is the value of the incident power on the load. So ಈ load ಮೇಲೆ incident power ಅಂತ ನೋಡುತ್ತೆ. So the incident power is not equal to this. What is equal is the incident power minus the backward power. Okay, should be equal to uh, the power that is delivered, okay, or the power that is absorbed by the load. So which is given by, which I had, that which is 0.5 watt. So what is P plus and P minus? That is a question. So I can see that I can write P minus. So this can be written as P plus, the forward power is nothing but minus times of the reflected power is nothing but magnitude of reflection coefficient square times the forward power. So that should be equal to 0.5. So this gives me that the forward power into 1 minus modulus of reflection coefficient square is nothing but equal to 0.5 watt. So all you need to know is what is the reflection coefficient at the load, right? What is the reflection coefficient at the load? So tau L is nothing but ZL minus Z0 by ZL plus Z0. So here ZL is 100 and Z0 is 50. So you get 50 by 150, that is 1 by 3. So if I do that, I get P plus into 1 minus 1 by 9 is equal to 0.5 or half. Okay, so it gives me 9 divided by 16. So that is so P plus is 0.5625 watts. So that means what is happening here is, in this scenario, okay, in this scenario, a forward wave is coming with a time average power of 0.5625 watts, and a backward wave is happening because of the reflection here. A time average backward wave is equal to 0.0625 watts. And when they subtract, so what is the total power that is absorbed by the load is nothing but the subtraction of these two, which is equal to 0.5, and this is the maximum power you can get, right? So that is how you need to understand this problem. Okay, so we'll move on to the next question. I think we have solved this question in the classwork, but anyways we'll solve it again. So in this problem, the line is a lambda by 4 line and it is a lossless line again. So what is given here is the incident power and the reflected power are given. So they're asking what is the value of Vg here. So what is the value of Vg? The value of Vg is the unknown here. What I want is particularly the magnitude of Vg. Okay. So to get that, what I can see is what is the power delivered here. So what is the power delivered here or the power that is absorbed here, okay, the power that is absorbed by the ZL load is nothing but the incident power minus the reflected power, so which is nothing but equal to, I can say that its value is 0.49 minus 0.09 watts, which is 0.4 watts. So this is the power absorbed, because this line is a lossless one. Okay, this is a lossless one, so nowhere power is eaten up. So whatever power is delivered at this port will be delivered to the load. So the power that is delivered here, okay, so that means the power that is delivered there should be equal to the power that is absorbed by the load, that is equal to 0.4 watt. So what is the power delivered at this terminal? At this terminal, how much power is delivered and తెలియాలంటే at this terminal what is the impedance I have? I want to know. So because it's a lambda by 4 line, so Zn is nothing but Z0 square divided by ZL. So the Z0 square is 50 into 50 divided by the ZL is 125. So we get 50 divided by 125, you get 20. So Zn is 20 ohms. So if Zn is given as 20 ohms, I see a 20 ohms here. Okay, so then I ask you what is the power that is delivered. So the power that is delivered is nothing but real part of half times of a real part of, so I can see the circuit is like this. So the circuit is like this, Vg, and there is a 20 ohms, and at the input also there is a 20 ohm. Okay, so I'm asking you how much power is delivered to this load at the input. So because this is also 20 ohm, so I have to calculate the real part of it is V into I conjugate at this input. So at the input, what is the V value? The potential is nothing but 20 times Vg divided by 20 plus 20, right? And what is the uh, current I? The current I is nothing but I conjugate. I have to take I conjugate is nothing but Vg conjugate divided by 20 plus 20 conjugate, whole conjugate, because it's all a real number. So you basically get half times of real part of 20 times of modulus of Vg square divided by, so 20 plus 20 is 40, so you get 40 square. So everything is a real number, so this simply becomes 2, so I get modulus of Vg square by, I can see that it is, I can write this as 8 times of 20. Okay, 2 into 2 plus I take a 2, I get 8 times of 20. So why did I write it specially like this is because as you can see that when the Zn is equal to 20, which is nothing but equal to Zg conjugate, which is also equal to 20, right? So there is an input matching. So what is the power delivered is the total available power. We have previously done it, but if I use the same formula you might get confused, so I didn't use that. I have derived the value which I'll get. You can see I get the same answer, Vg square by 8 Rg, which is 20. So the power delivered is given. We get the power delivered as 0.4. Okay, so from here I can say that 8 into 20 into 0.4 is 64. Okay, so that makes modulus of Vg square is equal to 8 volts. So that is how we solve this problem. Okay, that is all this question.